screen, and apparently there was a participant. Okay, so in theory, we should be ready to go. Hello. Okay, does this let you see something, Olivia?
I got it.
Okay, excellent. So if you have any questions in the chat room, just like type them in here, and I'll check this periodically to make sure everything is going okay. Okay. Excellent. So. I don't usually back. Because you're on the computer. People. Or excellent. I don't know people. So if you can just put your first, last, and key name on this room, thank you. And maybe you can make sure that it's passed it out. So this is a pretty, I should have learned the last sentence, so you guys don't have to worry about it. I'm not a teacher, I'm a coach. So I figured if you were going to get something out of the lecture, you would have passed it out, right? So I want to open the floor to you guys for questions as much as I possibly can. And if you guys want me to just try and take a little bit more direction, I have multiple ideas to this. I assume you guys all have questions. Try to do that. You know, understanding perfectly sequence series, how they all derive is pretty off the ordinary. So, do you have any questions right away? Or, yeah.
Just the differences between all the sequences and series. I honestly, we're learning that now. I have no idea.
Okay. So, what does it mean to be a sequence? How is a sequence different from a series or just a regular number? Or okay, so we talk about A sub n, right? There's A1, A2, all the way to AN, right? So this is a list of values, right? So what is a series? Okay, that requires us to have the sum of something, right? So that's A1 plus A2 plus A. Okay. But underneath that, there are some popular series also, right? So what are some of those? T-series. What else do we have? Two metric series. Okay. You guys see any other ones?
Harmonic.
Okay, so, you know, that's technically like a subset of this, right? Harmonic. And then we talk about like power slash K1. They're a special case too, right? They're usually going to involve these aren't all like mutually exclusive, right? We can have P series, but also alternate, or we can have, you know, so well, there's that distinction kind of way. So, or is that, yeah. Okay. So that's kind of the basics for what we want to talk about, right?
McCord is the Taylor series, right?
Yeah, so that's technically another slash here. Good point. And the difference is, yeah, where they're centered. The Florin series is always centered at 0, whereas the Taylor series is centered at some A.
Okay.
Hey guys.
Oh,
Okay. So that's just kind of a brief overview of what we might want to talk about. So this is bringing the three different series. What are your favorite what's written on this piece of paper? Alright, you guys? And it's just one bit, so we're just talking about what is the sequence, what the series is, and the types of series, right? Okay. So, do you have any specific questions you guys want to talk through?
just series. How do you know that they're different?
Well, to start that, how do we know of a sequence? So, yeah, go.
I don't know, I feel like it's easier because you could divide by n, or you could do less things.
So if we have the sequence AN, we say that this is inverted if this approaches some value, right? So like a specific example, 1 over n is AN, right? So if we take the limit as n goes to infinity of 1 over n, what is that? Yeah. So that implies this is inverted. I'm glad you asked that. So when we talk about the sequence, all we're worried about whether it approaches a value, right? And this approaches a value. When we talk about the series, we're trying to talk about whether the sum of all the terms are approaching a finite value, right? So while this approaches 0, it doesn't approach 0 fast enough for the sum of the terms to approach finite value. It takes a little getting used to. But so let's try that out. This has the harmonic series attached to it. A series, which is the sum of 1 over n. Okay? And this diverges. Because so that's kind of a loose term, but this is why we have all those tests, to try and help us restrict what it means to be fast. Right? I know this is kind of a little sloppy for this, but is everybody okay with this? So, we're going to talk about what series of conversions, right? So let's try and talk about a couple of the tests that we have available to us. So specifically, P-series. We just talked about the harmonic one, that it doesn't converge, right? So general form of these P-series is that we have 1 over n to some power p, right? So what's the rule for when this converges? Convergence if p is strictly greater than 1. And divergent. Right? Any questions? So what else did we have? Well, we talked about alternating series, we talked about geometric series. Let's talk about geometric series first, right? If we have geometric series, what's the form for that? And we know in general for when it starts at 1 and goes to infinity, right? What does that equal to? And in general, most of the time we can't tell what a series is actually referring to. Those ones are very basic. So it's important to remember what the form of this one is, since it's basically matched up, right? There you go. Right, excellent. So, this also ties into the ratio and stuff. And like your R series reduce the convergence comes in, all that good stuff, right? Okay, so let's maybe talk about an example of that. Can you think of an example? Okay, so says find the value of x which the series converges. Find some of the series for those values. Yeah, it is. It kind of came out looking like a lumpy thing. Okay. I don't hire me, so I understand. Right. So we want to talk about this one. There are a couple things that we want to notice first off, right? Like, where's our index start? So technically we can't apply this formula until we have an index from 1, right? So we have to shift that. And then we have to shift it.
What are you looking at?
Okay, yeah. So the idea is that you want to think about, this is just one big sum, where we're plugging in different numbers for n of time, right? So you could write this as 4 to the 0, x to the 0, plus 4 to the 1, x to the 1, plus da da da, all the way over here, right? And then it keeps going even because this is an infinite series. Okay, so if we are talking about the sum of 1 to infinity, that's just this part, right? So we can say that the sum of n equals 0 infinity, or 3 x to the n, is equal to 4 to the 0 plus, x to 0 plus the sum from n equals 1 to infinity. Why did it launch? Sorry. I'm kind of bad at smartboard sometimes, like things that I don't intend to happen. Alright. So does this make sense to everything I we know what this would be, right? So it's just 1. And then this only works. Okay, so that's also another good point that we want to make. When is this converted? When can we apply this theorem? Only when that's an excellent point to make. So we have to talk about where this, the geometric series, is going to be compared to. We got two things to the end. So that's kind of different, right? Is there any way we can make this be one thing? Okay. Together. Yeah, so this is the same as the quantity 4x together. So then we have to ask, when is the absolute value of 4x? Right? So this is x. Okay. So we say this is 1 plus. We do our formula, right? It's here. So that's 1 over 1 plus 4x. If, yes, you probably know this is. This is where it's convergent, and this is what it will converge to. Right? So, as long as we get that condition there, otherwise it's divergent, right? So, we want to make this something like that at the end. We want these lines there. I don't know if it's clear enough, but I think that gets working on what it is. Any questions about it? So this is essentially what it boils down to when we talk about integration of radius and
You got 1 over 1 plus 4 times that bit. What occurs?
well, it's true, minus. See?
What's us?
You guys all said you're confused and you gasped and decided to leave, but you didn't question me. Okay, there we go. That makes no sense, right?
Yeah.
Okay. Attachment. I'm fallible. Alright. Actually, you should trust me insofar as I can make stupid mistakes on Google Images, just like you guys. Alright. Any questions about this? Okay. What do we do?
I think so.
Alright. What do you got?
Sun from n equals 1 to 3. 6 times the negative 1 to the yeah, then Lx times f.
Okay, like the whole body, or
Like that. Well, this was due like a week and a half ago.
okay, no.
Yeah.
Alright, so you want to talk about what we're trying to do, radius and convergence of this?
Yeah, find the radius of convergence and find the interval on the
Okay.
convergence.
So, what do we want to do here? So, we have found the radius. Okay. So this is where something like the ratio test is going to come in, right? So how does the ratio test work? less than 1. I have a notation. So we have that. I was just looking at it, and I'm seeing that I would Do you really read your books anymore?
Those, let's see.
Okay. I suppose I only had to carry mine for permits, so.
I was supposed to the one that it's absolutely religion.
So it's. Alright. So now that we have our ratio tested line, we'll kind of write what we're doing over here. So, what is this going to look like for us? We want to make sure that anywhere we have n becomes an n plus 1, right? And then we're going to divide that by the same thing. Both of that. So from there, we can go on our fixing, right? And we could do some reducing. Like we could take the n out of both of these and both of these. So you just take both of these and cancel. You have -1 on the top. And we still have n plus 1, and we still have x. And that's just over n, right? So, because this has the absolute value, this negative is just 2, right? So all we really have is n plus 1 x over n, which gives us what? That's over n, right? So if we talk about an infinite limit, right? We have equal degrees n on top and bottom, so all we're looking at is the coefficients, right? So we have an x as a coefficient here, and we have a 1, so we just get the absolute value of x. Does that make sense? Okay. So now, scroll a little bit. We want to talk about the radius of the curve. So this means the values that make this true will have the form -r to r, right? So we call r the radius. right? Um, I probably shouldn't say this here. So, we talked about how if L, whatever this is equal to, is less than 1, then it's absolutely convergent, right? So all we're saying is this has to be less than 1, right? So what values of x satisfy this? Negative 1, which implies r equals 1, which never makes sense. And then, yeah, anything like that. So that's why I was like, let's pause. That's why I was going to fly into it, but I want to make sure everything's okay with this so far. Okay, so the last part is the interval convergence. We have to test the endpoints. Any of you guys talk about this? How many of you guys have done these classes like here? Okay, Ellis? Okay, that's the other one. There you go. I couldn't remember the last one, sorry. So the interval of convergence, we just want to check whether our original series is going to work if we put in one. So, like, if we talk about putting in 1 here, this whole term is just 1, right? So then we just have the series n alternating back and forth. Is that going to converge? So that would be a case where you would apply alternating series test, right? We'll come back to interval. We'll come back to it. So because I just kind of segued into it a little bit, let's talk about the alternating series test. It tells us that we have a series that has alternating terms. This is convergent if the active value of the sequence so, example. If we have a sum of n equals 1 infinity, negative 1 to the n, 1 over n. Okay. We know this isn't absolutely convergent, right? Because that brings us back to the harmonic series. So, not absolutely convergent. This is harmonic. But, because this is alternating, all we need is for the sequence 1 over n to converge, which I think that's what the very beginning does, right? It is conditionally convergent by the alternating series test. If anybody abbreviations get confusing, let me know. Right base equals Q, and then it's sloppy and better Q. As well as your fit. Any questions on that? Okay. Everything is still good over here. Yeah, no questions. Awesome. So, if we go back to our this thing. Now that we've worked with the implemented series test a little bit, we can see that this is the same kind of thing, right? We have, once we take out this x term, all we have is 6 negative 1 to n, right? So the absolute value of our sequence is just 6n. So is 6n conversion? No, right? So because of that, we know that 1 is not included in our area. So what about negative 1? If we put another negative 1 to the end here, what happens? Well, we have negative 1 to the end, negative 1 to the end, which is just 1 to the end, right? So we just get 6n again, which is still not included. So interval is still negative 1 and 1 because series 6n whatever it is and sequence 6n. We can use some more examples of that now, but it's not going to Okay. So if we press on, we can call this M3 dollars. So in this case, I'll try and figure out where this has a conversion, what the variable conversion is, right? So what do we do? But I think it's still going to end up animation. So that's another alternate way of expressing this. Okay, again, here's your test. That means that we get the value. And then dividing by a fraction is the same as multiplying by the reciprocal. So when we go through the AN term, we just get n equals over the top. Okay. So now we can do the same thing here again, where we can take all of this in the n term. So we're going to very importantly. So we just get negative 6x times n with 3x over n plus 1. 3x. So, what are the mechanisms? What do we actually got in there? Because it's the same thing again. N has the same degree in time time, so you're just looking for coefficients thereof. Coefficient here is negative 6x. Coefficient here is 1. Right, that 1 is a value like that. So then, in order for this to converge, what do we need? This then has to be less than 1. So, the absolute value of x, 6 has to be less than 1. That means that the absolute value of 6 has to be less than 1. So that means that R is what? Well, what x are you going to make this to? Right? So what's the radius?
Is that two value is actually one third or two?
It's one. Okay, so that means that R is going to be 1/6. And then you can test our endpoints again to see if they will work. So this one's going to be a little different than that way. So if you put in 1/6 for x here, that's going to be called negative 1 to the n, right? Which means we have an alternating p-series. And the p-series by itself has to break up. So the alternating one is 6, right? So let's check 1/6. Then we have negative 1 over n 3,000. And we know this is perfect, right? And then if we check negative 1/6, that's going to be a positive 1 here, right? So is this going to be just 1 over n 3,000, which is also important, right? Let's see what that is. Okay, so that means that our interval of convergence is actually going to be inclusive of both ends. Any questions? So, anyway. I appreciate that. Power series? Okay. So what about power series? Like, where it comes from, how it would be another equal, equal. Well, anyway, so what are some common examples of power series? Well, let's start with that. Like, what's a common power series, right? Okay, so what if we wanted to make one of I'm curious on the coming back to the middle. So if, like, using this fact, can we convert this into a power series? So how might we go about such a thing? Yeah, other than one of the very questions, we go by very carefully. All right. Well, what are some? What are some differences between here and here? They both have one on the top, right? So that's not it. They both have one here. This is where we start having differences, right? So you might say that negative x in the first one is equal to x cubed in the second one, right? Which is the same as saying x is negative x cubed, right? Okay. So here, x is negative. Because that is so then you might want to rewrite that, or you might not. If you did, you rewrite it. Yeah. So, any questions? So, new question. How did we arrive at this conclusion? Why is the power series representation for polynomial manifest or XPN? Okay, so it is a geometric series, but that doesn't explain why it's associated with polynomial. Where did we come up with the idea that this function is representing x? Okay. Yeah. So, because, well, we have to do a little bit of jumping around it, right? It's from 0.
Oh, that's right.
But, yeah, that's the idea. So it's you can kind of see where they're coming from. And there's actually, like, what am I going to do with different options? Like, you know, yes, I guess it's not maybe we get that.
Magic.
Right? So the idea is something called the Taylor series, right? That tells us that any polynomial, well, slash or series. See, that's why I read it so long. Alright. So that tells us that any function can be written as and in case you're not familiar with the notation, this means the nth derivative evaluated at a. So this would give us the Taylor series centered at a. I'm going to do this to the sheet, so if you don't have it, don't panic, I'm going to write it again. So let's just start with series or so you might want to pick an FX, right? So let's see if we can get where the EDX came from, right? So if we have EDX and our FX, I usually end up making kind of like a little chart for myself. So if I say this is N, and I want 0, 1, 2, 1, right, 1 twice, 2, 3, okay? And then I want that N of X, so what's my derivative? And then what is my derivative of value equals 0? If you're really clever, you don't have to draw this chart. I just like to draw it because it makes me look nice. So what's our zeroth derivative? Well, that's just our function, right? So in our case, it's e to the x. So e to the 0 is just 1, right? So what's our first derivative of e to the x? Yes, right? Oh, it's so easy, right? So we just get 1, 1, 1, blah, 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 right? Okay, so now what we want to do is say what's the nth derivative of 0 over n factorial, right? So 1, excuse me, over 0 factorial is just 1 over 1, which is 1, right? 1 over 1 factorial is 1 again. 1 over 2 factorial is 1 half. 1 over 3 factorial is 1 over 6 factorial, right? So, all that is still just times by x to the n. So, we say that this is equal to 1 plus x plus 1 half x squared plus 1 to 6 x cubed plus 1 half, which, when we calculate, is after the scratch. All right. So, oh, sorry. There we go. What was it? If I was slowly writing my hand, it was going to be we are going to do a slightly simple altogether. So, that means I'm not going to write anything in my own, just tell me what you like. I know. Okay, I'm not listening to the lecture, so this is your participation. I could be really cool and maybe you guys all come right parts of it, but I'm a nice person. If you really want to come right, I'm not going to stop you. Yes, exactly.
When it starts writing, it's taking up my own copy right now.
Yeah.
It's terrible.
There you go. Everybody done copying this stuff? Alright. So, then let's go. Let's take it. So, what if we have something, what if we have something like sine? Well, we're just trying to find the power series, right? So we try to find the Lorentz series of sine x. So, you guys like the chart?
Yeah.
Like the chart? Makes sense? Alright, well, I'll just go with chart. Alright. So what's supposed to go in this column?
Values.
So, our derivative, right? So, what's x0 of x? So x. Okay, and then, and that's where we use right? So that's going to be pretty handy. So now, what's this third column? Okay, so what do we get? Zero. Okay, so now, what does our series look like?
Minus x2 over n x2.
Which is, yeah. So, okay, so then what do you think is going to come back around, right? Because we got the sign of n, so what am I saying with you?
X over 5x2 minus x2.
Cool, now we get the idea, right?
Yeah.
Okay, so how do we write this in one half W? There are two schools of thought on this, right? Either we use kind of an improper index and we say we go over the odd numbers and do broad. But if we didn't want to do that, right? Say we still want to start at n equals 0. How are we going to make it so it only picks these odd ones? You know it's that something. Really got the benefit of having, how to figure this. I've gone through it. What's going on? So if we do just n plus 1, then this one is first, right? What else can we do to try and get 1 when we really need 0? You're thinking? Okay. What if we did like 100 n plus 1? That's still 1, right? So what would we need in order for this one to work? Because now we're not so worried about this one. If we put in 1, how are we going to get 3? We always got to have that plus 1 for the first time, right? So if we put in n, we want, n equals 1, we want 2. So what if we thought about it as 2n? Does that work for the next one? So you can represent an odd number using 2n plus 1. You know 2n is always going to be 2n. And the next one is 2n, right? So then we'll do the same things for our powers, because we want them to match, right? But now, we want to account for our negative. So how is that going to work? So if we plug in 0, we want it to be positive. If we plug in 1, we want it to be negative. Or positive. Okay? Yay, we're going to science.
Choose scroll.
Okay.
Okay.
So do we text? Do we text questions? So, you guys have to like the body body because in general, if you can come up with representations for these series or for these functions, well, let's say we're doing an insult where it doesn't work out for half the time, but it will work out for half all of these functions. It's going to help us make impactful relations. Close. Those are numbers, okay? Yeah, I got it right on the script, so I can say what you did. When I come to the but in the you absolutely there's a major section that we just got now. And like another how to do a bunch of series of and the makes some sense. I would shift it from really much to okay. So while we're waiting, so the question was conditional variables versus absolute variables. So if we let's say that absolutely that means that the sum of the absolute value of the if the sum of n equals 0 is infinity, it's conditionally convertible. That means that the sum of n equals 0, yeah, value of n is divergent, but the sum of n equals 0 is convergent. By alternating the series test or similar. So, so, like, the standard example again is the 1 over n, right? So look at this one. 1 over n. Is conditionally divergent because when n is 0 n is divergent. But by alternating the series past the sum n is divergent since limit So,
Have a good night.
Here you go. Do you have anything?
Still no questions in the chat thing, so.
Alright, so you guys feel like you guys are trying to talk about creativity?
I put back is equal to actual law.
Oh, sorry. No, you guys are not.
Have a good night.
That's awesome. Wow.
Have been amazing.
That sucks.
She goes, it's so weird. Oh, okay. Was this happy? Yeah. Okay. So, this is what I'm
It was good.
in a chat.
Good please.
Um,
F of x is equal to the natural log of I1 plus 3.
so we want to find the Taylor series for this?
Yeah, and find the associated radius.
Okay. So, how might we go about this?
Well, for 6.
Is it 10? Is it that 10?
Yeah. She's perfect.
Can we make the chart?
Yes.
I don't make any mistakes. Chart's fine. Look at that one.
The Taylor series is considered or something?
And it was 1.
It must be 8. Oh, so after this, we're going to actually do a Taylor series instead of a Florence series. So, what do we got? What's our 0? And first derivative.
3 over.
And then our second derivative.
comments for?
So, you want to, this -2 you draw down, so it's going to be positive 18 plus the 3 from the inside, right? So 18 times 3 ends it over to 54. Yeah,
What-
it would be 9.
Someone has a question. Wait.
Two convergent series, add or subtract. Okay,
So can anybody see this or feel it? So if two convergent series add or subtract, can I say that the answer series is convergent series? Right?
so we say the survey says yes. And that's essentially because, like, if you take each series, right, they're equal to a number, and you can add numbers together and still get a number, right? Okay, excellent. I know, but I was still... I'm like standing in the way for you. Oh.
This is an Adobe Connect, so if you guys didn't feel like facing your own to come here in a minute, like a good quick. Yeah, it says on the email. Yeah. Oh, yeah. So whenever you do an exam review or an SI thing in the RTD Adobe Connect, so you have to be able to physically do your session and all the files. So, you know, in theory, because I'm recording this session, you'll be able to hear what I said, see what I wrote at any time. So if you go back to this, like on the archive site, you can be like, oh, what the hell was she talking about when she said this, this, and this? And then you can look it up. I know.
Okay.
The important thing is that I made a mistake. That's her on my study. I know. Got to follow through the rest of my I'll just overdo that girl on the internet who lost her like this. Okay, so. Okay, so let's just go with these first 4 terms here and see what we've got. So if we start plugging in 0, what do we get? And this one's 0, right?
No, it'll be the next.
So now we want to see what this looks like. Okay. So our first one is 0 over 0, right? Plus minus okay.
Need to send over to get one.
Yeah. If you need to find the signal location, that's where you have to detect that pattern. And this is, I feel like the hard part is where it's
Button.
and then we're going to put the best again, right? But there's another coefficient that we can put here. Right? But then we would then have this 3, 6. And we do that. What else is it? Like, you gotta think about this stuff, right? So, how did we get from 9 to 16? Okay. So, how did we get from 3 to 9 we multiply by, Okay, so why did you say 3x?
And then you're multiplying by
Technically, that power is negative x, right?
okay,
Yeah. So,
negative, okay.
oh, we need to make sure this one's positive, right? So this is the answer one. I'm gonna move my thing a second, right? Okay, yeah. Okay, so let's just double check everything, make sure it works. If you put in a 0, you get positive 1, right? This isn't right, right? Oh, but that's a 0. Okay, that's right. And then we put in a 1, we get negative 1 squared, it's positive 3x to the 1 over 1 factorial. If we put in a 2, we get negative 1 to the third, which is negative 3 okay. So that would be a 6, right? But then that would be a 54, right? This is where you have to pass my diagram. So, and like you only really always have to check. You would if you're right, you could make a mistake. So, yeah, so from here to here, it's 6.
It's gonna be,
Yeah,
Nine.
we didn't compute the both.
I mean, it's gonna be,
We're gonna end up multiplying this by negative 9, right? Yeah. So the next one will be 9. So maybe it's not 3 times n, but
3x3.
3. Well, I'm still gonna, I was just keeping the
Oh, okay,
format.
yeah,
So now does this work?
yes.
So if we plug in 0, now we get 1 here, though, right? So that's not cool. So the first term doesn't work.
And that bigger than this, like, if we get like that, when we expand it, I think it should be more. I think it's a bigger than
I feel like we got so far off. Well, okay, because what are we doing each time? I think we can talk about it. Each time we take this, the 3 that we have right here and multiply it by our exponent, right? So like, we do the negative 1 times the 3 here we have times the 3 inside. So each time we're tapping on a 3. So you're going to have like a 3 to the end of that, right? So, if that's the case, that was times negative 1, and then we have 3 to the end, which is 3 to 3 is 27
Wait, we're ending.
times 2 is 54, right?
Does it end equal 1?
And, yeah, and will equal 1.
Like, what's some, like, different bits?
1?
Mm-hmm.
I mean,
Let's-
you could start
no,
at
that's
1
what it
because the
says
first
here.
term is 0. Then I guess that would be easier to do. But it should still work either way, right? Really. Alright, so let's try this one. I mean, obviously, we're going to You could do that. Which is not a big deal. Okay. Well, okay. So what if we start this at other people? That's literally. So if we started at 1, then we're not worried about the spelling, right? So at 3 again.
Is it really? No.
This must be the exact same.
We can see that now. Is the 54 right thing in anything?
Yeah. Yeah, this is so recording because I was puzzling over this.
Yeah, but then
Don't you look Don't you look
Yeah, that's great. So that was so that's the six is spelled. Okay, so we want whatever we're multiplying by to multiply by 3. Or to add 3, right? The next one we have.
oh,
This is on this first step, we want just 3, right? And then when we add, if this is 3, because if this is 3n, then that gives us 6, right?
plus 2, so 3 and plus 2. Yeah, because then it'll be 3, so 3n plus 3 would be then 6, and then I think it's
No.
3 times that.
Okay, so let's just try to come back to this once we have a little bit more time to have a chance to at least do the Taylor series. Because I can start this all day and not do this thing. Get that out. So Taylor series.
Before we go to it, we'll have
Yeah. So Taylor series, it used to be the same thing, right? So we would be able to center it with something else. So if we want to use an example that we've already done, right? Say we want to use EPS centered at x equals t. So, there. So, because our root is functions are offset. So when we plug in 2 this time, instead of just getting 1, we always get t squared. So that means that what we end up with is that u of the x equals 0 and e squared is each one of those, right? So how do we make it be each one? Because if we want it to be, it should just be on all of these already. So for these should be Taylor series, right?
So Taylor series, you should include like the word sentence
Yeah.
and all of the next stuff.
So instead of having an act, it's just something with an act in it, this doesn't change, it's just so we don't have to, finding the pattern is a lot easier with the same number every time. So it's pretty much just a Taylor series, just give the evaluate the different value, see what's done. Yeah. So. So, unit test, right? Do you have an example of how your letters you want to talk about, or? Do you have one you want to talk about specifically?
I mean, not specifically just recognize, but I think they would like to do it.
Do you talk about the error boundaries or something like that?
It's sort of, yeah, that's what I don't.
So, just for a state of the record, what is the input class?
That's,
Very clever. So, integral system, and then I say Fn, An, probably one. Okay. Then we have the integral from on f of x instead of f of n. Can you read that? Or is that just what you do? Okay. So if we say that the inside stuff is some f of n, then we can compare that to an f of x, which is continuous x, so it's an f, right? And then we would integrate from 1 to infinity, that's the series one. So if this is converted, so if this is conversion, then the series is conversion, right? So if it's backward integral, then the series is conversion.
So to summarize, and from n to the 1 n squared to the negative n.
What's that? Okay. So obviously first you want to do your test for divergence, affecting the limit and that goes to infinity this thing is 0. It is, so you go on to the next thing, which is probably the integral test, or yeah, you would say, okay, it's not a P series, it's not the E in it. You would say, okay, it's maybe a comparison I could do, but it's kind of messy. But in this case, it looks like it would be easily integral. So we use integration. Can you please pronounce that word? I don't know. No, you don't, but yes. Like somebody wouldn't believe me that asymptotically is that I think that. Yeah.
Negativity of
Okay. Anyway, we got sidetracked there for a second. So we would evaluate the integral of x squared and the negative x squared. Yeah.
As
So-
B goes to
Technically, right? I do R in this.
one more.
Okay. So we want to use like substitution, right? Use negative x cubed. So we would use that x squared. Yes. So that means we have the limit of r goes to infinity. We put in 1 and negative 1 to like r. So
Are you changing what it's
I am.
so
So this, like, I guess that's still half, but. You just can't write in the lower bound because it technically doesn't apply to the variable for the top. So if you don't want to change your limit of integration, you just have to denote that you have like a placeholder for that lower limit because infinity is infinity. Infinity is not going to be like that. I seem to have to go to negative infinity. Anyway, so let's just assume you didn't want to change your variables and then we're going to come back to it. Yeah. So actually we can put it right there. And then,
Okay, so if we plug in and we try and take that limit, right? Or not X.
Wait, you don't have to integrate maybe what for you.
It's just, if you can take it out of the building and just put it in
Oh, yeah. Good. Sweet.
So then, we notice that our limit is going to equal 0, right? So we just get 1/3. This is less than infinity, so
You said, what's the limit of that?
of this thing, 0. Right, it's essentially like having 1 over e to the infinity, which is going to get really big if we simplify it. Okay, word of caution. The series does not converge to we just know it converges to something. The integral that we're comparing to and the actual series itself are not equal. It's a comparison with the integral of continuous function. There are values that we could touch with this integral that we can't with the series, so they will not have equal values. It just goes to, like, it stands to reason that if we had more values in the real we add each other.
So we have that.
No, that is just for your point of reference. Don't say that the series converges to a number of the integral. The integral tells you whether or not.
Is there a way to find out what it is?
Not really any other things. But that's what I was saying. Usually we don't know if the things converge to whether or not they are.
They can do, S n plus 1 is equal to S n plus k n
So
plus
that's the error value.
1. Yeah, yeah.
Yeah. So,
Don't have fun.
okay, so the actual bound that we gave you, because I know, like, in general, we can say SM plus
That's what I'm thinking.
say. Or do you have like an example that you want? I would rather just use it.
I mean, I have to go with.
So say we're talking about. We want to estimate we want to get the first time hurt, and then we want to estimate the area involved in this classroom. Right? So we talk about. But I mean, technically, we don't keep doing it all stuff, right? So it's which means that's not just bonus to the scale. And since that was this thing, if you say R, well, I guess, yeah, so Rn in this case is less than or equal to 2. So like if you're doing the
What the,
R is the your estimate. So like if you were doing the remainder after you approximated the first 10 terms, then you would say that remainder is going to be less than 1 over 200.
yeah. Yeah, the one thing you wrote was, estimate, kind of what you wrote, but instead of estimate, yeah, estimate was R of the.
Yeah. Yeah, that's good.
So then there's a
This
problem.
one, right? If you add SN to all of these, you get what you said.
So there's a problem. So,
He said he could include that formula. So basically what you would end up doing is you would say something like, how many terms might you have to evaluate in order to have your error less than 0.01? And then that would be the remainder of the So you would figure out, you would like figure out in general what this would have to be. So like, you might say, error less than 0.001, right? Then that means that what we're doing inward is where 1 over 2n squared is going to be approximately 0.001, so that we can use that as a bound, right? So actually we want this to be greater than or equal to 0.001 in order for that to be true. Okay? So then you just solve for n and figure out how many terms in series you have to evaluate in order for your error to be small. That would be one way to fix it. That's the most common in ours.
It's pretty built.
It's figuring out how
should get the final exam and then teach it.
teach it.
Every
That's it.
every teacher.
We're not recording this.
Yes, we're going to this. No, it's really bad idea. Actually, it's really terrible because then you don't even learn anything. You just And school isn't supposed to be about how well you memorize things. Okay, tissues. Okay, here's like 15 minutes. You guys have any other last questions?
Pretty good, actually.
And we'll be back again next Monday, sometime always. But if you guys come up with any questions between now and then, make a note of them so that we can talk about them.
Is it gonna be the same subject?
Yeah, more or less, and then possibly more about like reviewing active for your final as well.
Okay.
So like if you had something from the video session, some puzzle you bring that in. We'll cover this again, but hopefully we won't have to do 2 hours, to 2 hours and stuff, right?
Yeah, like parametric equations and polar curve.
Okay.
So the first question.
Awesome, thanks for coming, you guys. It was really
Thank
great.
Any other questions last minute from the online section here? I don't even know how many people are in that right now. Yeah.